Hi there. I'm here to talk about a human-in-the-loop framework for test-time policy adaptation. Consider a robot that has been trained to put salad in the bowl from watching demonstrations in a factory. Now, when we deploy the robot in a user's home, the policy may fail. This is due to distribution shift, where certain properties of the observation may have changed from training to test time. Data augmentation is a technique that can help policies be more robust. For example, if the user thinks of all bowls being the same in their home, we can leverage the fact that the bowl texture is an irrelevant concept to then recycle actions that we've already seen before and create many new demonstrations. Unfortunately, if the human thinks of the salad bowl as only being wooden, as is preferred in their home, we would not be able to do such augmentation. This brings us to the main question asked in this work, which is how do we know which visual concepts are task irrelevant and able to be augmented? Our key insight is that end users are uniquely positioned to tell us what concepts are task irrelevant. How do we actually get this feedback? Let's consider a naive solution, watching the robot fail. In the previous example, had a human user seen this behavior, is it the bowl texture that's causing the failure? Is it the salad positioning? Is it some other thing completely unrelated to something the user is able to observe? Typically, watching black box model failures is not informative to understanding the true source of failure. Our idea is to explicitly provide counterfactual demonstrations. Now, what does this mean? Consider in the following example. If we had also provided a contrastive explanation, such as the robot being able to put the salad in the bowl had the bowl texture been changed, then the user would be able to better understand that bowl texture is indeed the problem, and potentially also identify that it's relevant for their task. In this way, counterfactuals explicitly isolate shifted concepts so that our human users can quickly and accurately identify them. We call our full framework DFA. In the diagnosis portion of our framework, we roll out a potentially failed behavior trajectory for a human user. We collect a single demonstration then from the user of what they desired the action to actually have been, and then we perform a search through the visual concept space to generate a counterfactual explanation that would have resulted in similar actions for the robot had something such as the bowl texture been changed. In the feedback stage of our framework, we then collect user feedback, such as whether or not the bowl texture is irrelevant and able to be augmented, or if bowl texture is actually very relevant to their task. Lastly, in the adaptation stage, we leverage this information to either perform augmentation of the irrelevant concept or fine-tuning from simply the collected demonstration. We evaluate on 3 domains, but for the purposes of this talk, we'll focus on VIMA, which is the most complex robotic control environment. We generate different control distribution shifts and ask users to identify the shifted concept. For example, we could see the following training distribution. Now at test time, we enforce a specific shifted concept, such as potentially the bowl being replaced with a pallet, and observe the failure from the robot. We then present a counterfactual, where had the pallet been replaced with the bowl, the robot would have succeeded. We do this for many other types of distribution shifts, such as new distractors and failed policies, including those that are both task irrelevant and task relevant. We first ask whether our method helps users identify the correct concept. As we see for object shifts, our method, in pink, is significantly better at helping users identify the correct concept. This is highlighted in other shift types as well. We next ask, does our method improve sample efficiency? As highlighted, our method, in orange, significantly outperforms our random-only and human-only baselines, improving the quality of performance of policy with the same number of demonstrations. In conclusion, our method enables more efficient human-guided policy adaptation by generating counterfactual demonstrations.